still, but hopefully everyone will enjoy themselves. Well, we're very pleased to have John here. John is visiting for a few weeks. He'll be giving a series of talks, which I think he's going to give a little advert for here. This is the talk that will kick those off. So a little bit about John. John's worked for the majority of his career at the University of California. For a long time he's been a mathematical physicist. In more recent years, or perhaps still calling himself a mathematical physicist, he's decided he wants to focus more on general issues, environmental issues, but with a particular mathematical bent still. And as part of that, he's working on a new research program which is network theory. And we're going to hear a lot about that today and in the next series of 3 hours.
Great, thanks very much. Well, it's great to be here. I just got here. I've been in Germany lately, so not too much jet lag. So I'm going to be giving a few talks on a subject I like to call network theory. And so this talk is supposed to be an overview of those. The rest of them will be on Tuesdays at 3:30, I guess here, same place. First one on electrical circuits and signal flow graphs, which are things that show up in control theory. The second one on things called stochastic Petri nets, chemical reaction networks, which are used in chemistry, epidemiology, population biology to describe interaction of lots of things, different kinds. And it turns out the math of those is related to Feynman diagrams. And then we'll give a talk about probabilistic aspects of networks. So it's maybe a bit about Bayesian networks, but probably more about information and entropy. So today I just want to sort of sketch the broad picture, which is a picture that isn't filled in by any means. There's a lot to do left, and I sort of want to recruit anyone who's interested to help out. So the idea is that in many areas of science and engineering, people use diagrams of networks to describe complicated systems made of interacting parts. And so these pictures you will find in widely diverse areas of applied mathematics. So here's an electrical circuit diagram. Here is an example of a stochastic Petri net, a particular one that's used to describe a model of HIV and how HIV infects blood cells. This is a little one from biology showing something called a repressilator, which is 3 genes, each of which repress the activity of the next one. And this is just a sort of sample from control theory, this study of physical systems where you are trying to keep the system behaving in some desired manner and you have some external inputs to that system. So there's some language of diagrams that people have found very useful in describing complicated systems. It's a visible language and it's very intuitive, and it makes it easy to imagine taking a system and taking another system and sticking them together in a way, connecting them somehow to make a bigger system. So nobody needed to think about the mathematical theory behind these diagrams to start using them. They were just convenient. But I think we now deserve to have a good mathematical theory of these because, well, many reasons. If you're a mathematician, if you start looking at enough of these things, you think this is some mathematical subject which deserves to be studied. But there's another reason, which is that people in different subject areas don't talk to each other enough, even if they're talking about very similar things, because they use very different vocabulary to talk about those things. So I found, for example, that chemists are proving theorems about stochastic Petri nets, which would be useful to people who are doing evolutionary game theory. And the people in evolutionary game theory don't learn those theorems because they're theorems about chemical reaction networks. And that phrase is probably just enough already to scare them off. So I've been trying to look at these different subjects and find the commonalities between different diagram languages and translate them into mathematics. Of course, translating something into mathematics is not a guaranteed recipe for making it comprehensible to most people. In fact, you might say just the opposite. So translating into mathematics is one step of the project, but then also translating back out of mathematics is something else that I think is extremely important. So mathematics may serve as a kind of clearinghouse of ideas, and its advantage is that it has a neutral language for talking about concepts, which doesn't lock itself into any one particular application. But of course, for that to be useful to people who are doing those applications, they need help in understanding the mathematical language, which tends to be more abstract than they're used to. So category theory has to be part of the solution to this question of what's the language of networks. And I think this became clear around the 1980s at the interface of two apparently different subjects, knot theory and quantum physics. This little slide here is an example of a proof in Louis Kaufman's, a paper by Louis Kaufman, who is a knot theorist who is using ideas that came from quantum mechanics to calculate new invariants of knots. And part of what's interesting about his work is that he takes diagrams very seriously, and so you could have a proof, and then the proof would consist of manipulations of diagrams according to rules which had been established earlier, and then say part B is left for the reader. And this is a somewhat new style of mathematical proof at the time. People had often thought of diagrams as a kind of heuristic aid to doing calculations. You can take any one of these diagrams and translate it into some more standard mathematical vocabulary, for example, linear algebra. But around this time it became clear that translating your concepts out of the diagram language was only making them more obscure, and that the diagram language itself really should be taken seriously. And so a lot of people got interested in the mathematics of diagrams at that time, and using category theory as a way to formalize that. Now, categories are clearly good for this because categories are a general formalism for describing processes. So by process, I mean something extremely general, anything where something happens and the happening has some starting point and some finishing point. So in category theory language, you don't say process, you say morphism. You call it a morphism from some input X to some output Y. Those inputs and outputs are called objects. So category theorists talk about morphisms going between objects, and part of the idea is that whenever you see any sort of diagram that anyone uses where there's some kind of black box, or in this case a blue triangle, which has some input and some output, that's a morphism in a category. The people using the notation may not know exactly what category they're talking about, but they usually have something in mind. And the point is that you can do one process after another if the output of the first one equals the input of the second. And that's the basic thing you can do in a category. It's called composing morphisms. So here we're composing F and G to get a morphism that goes all the way from X to Y. So those boxes there, they could be electrical resistors, for example. You could be sticking two resistors in series. That would be an example of composing morphisms. Or they could be computer programs that take a number as input and put a number out as output. In a monoidal category, you can also do processes in parallel. So there is a concept called tensoring, which is just setting two things side by side. And so if I have a morphism F from X to Y and a morphism G from X prime to Y prime, we can, it's just an arbitrary term, tensor them to get a morphism called F tensor G, drawn here, from X tensor X prime to Y tensor Y prime. So that's the idea of doing things in parallel. And the word tensor shows up because in linear algebra, one thing you can do is you can tensor vector spaces, which are objects of some sort, and you can tensor linear maps or linear operators between vector spaces. And so that example was so famous that this operation gets to be called tensoring. But you shouldn't think of it as being limited to that situation. Next, in a braided monoidal category, we move up from 2 dimensions to 3 dimensions. We have the concept of switching two objects. So we have a certain morphism called the braiding, which goes from x tensor y to y tensor x, when x and y are any objects in your category. So it simply says that in certain categories you have the ability to switch two things. And this braiding, we demand some axioms. I'm not listing all the axioms here, but it has an inverse, which just seems to be switching things again, but it's nice to draw it in the other way. So here, if we switch two things and then unswitch them, this would be the braiding in its inverse, then your mind is led to want to straighten out those things and get this. This is called the identity morphism from x tensor y to itself. That is the process where nothing at all is happening. And similarly, you have their inverses in the other order. So in applications of category theory to knot theory, it was realized that braided monoidal categories are deeply related to knot theory. A knot actually is a morphism in a certain braided monoidal category. And they were able then to use other braided monoidal categories to get invariance of knots. But in most of the applications that I'm interested in, it doesn't matter which strand goes over which. So that's called a symmetric monoidal category, where the braiding obeys this identity. So if you're trying to untie your shoes or disentangle the wires that you're dealing with when you're an actual electrical engineer, you're not allowed to assume that these are equal. The whole problem is that they're not. That's how things get tangled up. But if you're have the liberty of just imagining an electrical circuit diagram where all you care about is the flow of current, to a pretty good approximation, it doesn't matter which wire crosses over which, although if you think about it carefully, it actually does, because the current makes a magnetic field, but never mind that. You try to design machines where it doesn't matter who crosses over who. And certainly when you switch abstract mathematical objects, like two elements into switch an ordered pair, x comma y to y comma x, you don't ask which one went over which one. And so you say you're working in a symmetric monoidal category. Really what we've done here is we've gone up from the 3rd dimension up to the 4th dimension because in the 4th dimension you could untangle, you could deform this crossing to that one, because you'd have an extra dimension to wiggle things around. So the fact is that we do live in 4 dimensions, where the 4th dimension is time, and we meet lots of processes of switching things around with the passage of time, where it doesn't really matter who went in front of who, because we can continuously interpolate between the two ways of doing that. So symmetric monoidal categories are natural mathematics for creatures who encounter a lot of roughly point-like objects, particles, moving around in 3-dimensional space with the passage of time. And that's why they show up in physics so much. But they also show up in many other applications. So the category with vector spaces as objects, and linear maps between those, or linear transformations between those as morphisms, that's a very famous one. And you can use the tensor product of vector spaces to make it into a symmetric monoidal category. And this is the category that physicists in quantum physics use a lot, with some slight variations, like using Hilbert spaces instead of vector spaces. But this talk is so vague that that difference barely matters now. It matters later. So I will say vector spaces. And one of the great discoveries in the relationship of category theory and physics was realizing that Feynman diagrams, which particle physicists use to describe things like a proton and an antiproton colliding and emitting a bunch of other gunk, a bunch of other particles, those are actually pictures of morphisms in this particular symmetric monoidal category. Here we're reading the picture from left to right instead of from up to down, but apart from that, it really is an example of what I was talking about. If you look carefully at the math that people use in particle physics, you'll see that the proton has a certain vector space or Hilbert space of states. So does the antiproton. If you set them side by side in the picture, you have a system consisting of two parts, and you take the tensor product of their two Hilbert spaces to describe the joint system. And this picture is actually a picture of a certain linear operator from that tensor product of vector spaces to the tensor product of the vector spaces for all these other particles. And each of these little pieces of the picture, if you learn quantum field theory, you learn that it's a name for a specific operator. So we're building a big linear operator, or linear map, out of little ones by the process of composing, that is doing something after something else, and tensoring, doing two things side by side. You might also have the braiding. You might have two particles switch places. This picture doesn't show that. So when you learn quantum field theory, the word symmetric monoidal category never shows up in the textbook, at least not yet. Someday we'll have some textbooks that admit that that's what's going on. But when you are done learning it, you can see that what I'm saying is true. That this is a notation for efficiently writing down pictures of linear operators, but it's a beautiful notation because it's very vivid and because it describes exactly what it looks like it describes. It looks like this is a picture of a proton and an antiproton coming in and then shooting off some weird stuff, and it smacks into each other and it shoots out. Well, that's really what it is. That's what's going on. But the beauty of our world is that our world is actually made out of linear algebra. So when you ask, well, what is that proton really? Well, it's really a vector space, the vector space of possible states of the proton. And this picture is an operator. So that was Feynman's brilliant discovery, one of them. But I don't think particle physicists should have all the fun in using fancy math like category theory to do their business. After all, I think last century was really the century where physics was the defining science, science with the most revolutions per minute. Now I'd say it's the century of biology, and that's true for lots of reasons. One is that we know enough physics so that we feel completely confident that we have enough physics at our disposal to describe the behavior of molecules and thus in principle of life. But translating from in principle to practice is going to take at least a century, probably more. But second of all, we're in a century where computation has reached the stage, due to technology developed through physics, that it can do the immense calculations required to study more complex systems, like biological systems, instead of just individual atoms. But then there's a third reason, which really got me pulled into this, which is that we're in the midst of a kind of crisis, which is actually much more than the crisis of global warming or destruction of ecosystems. It's really the Anthropocene, the period in geological history in which humanity is starting to radically affect all the cycles, like the carbon cycle, nitrogen cycle, so on, in the planet, and we're reaching the point at which we can no longer pretend that nature is big and we are small and we can do pretty much whatever we want to do. Now we've reached the stage through our exponential growth in population and advances in technology where we are as big as nature, and that means we have to adopt a new relationship to nature. We need to really understand nature and not treating it as a blank background upon which we can do whatever we want. Or we'll destroy our own civilization. The planet will survive, but our civilization might not. So I think we should do everything we can to adopt this new relationship to nature that we need to reach some kind of happy future. And I don't think mathematics is the main ingredient in solving these many problems that we face, but unfortunately I'm just trapped in the body of a mathematician. Actually, I'm trapped in the brain of a mathematician. And so after thinking about this for a while, I decided I'd better do what I'm good at, which is mathematics to some extent, and see what I can do to get mathematics involved in this grand issue of our relationship to the planet. So back in the 1950s, a visionary fellow named Howard Odum introduced something which he called energy systems language for ecology. He was an ecologist. And he has a beautiful book that's full of diagrams like this. He started drawing diagrams like these to start trying to visualize ecosystems as flows of energy, flows of water, flows of other conserved substances like carbon and so on, and to model ecosystems in quite elaborate detail. This is not very elaborate, but he made a model, for example, of the whole Chesapeake Bay, a bay in America, of this sort, where you have different things flowing from compartment to compartment, interacting, regulating the rate of flow of other things, and he was trying to understand all the questions that ecologists want to understand, which is when are situations stable, when will changing something cause a dramatic change in other things, and so on. But he was using this language for ecology. Now, he was a bit ahead of his time, and it didn't really catch on too much at that point. But nowadays, biology is a much more advanced science. It's advancing very rapidly. And nowadays, biologists use lots of kinds of networks to describe many different complex processes. In fact, it's gotten to be so popular that there's actually a project called the Systems Biology Graphical Notation Project that's trying to standardize the different network languages, because every biologist has been making up their own style of diagrams, and they realized that it was becoming very difficult to understand what different people meant by their diagrams. This is only one aspect of biology. Systems biology is, for example, not including what we would call ecology. It's mainly about molecular biology, but it's not about it's not about studying individual molecules so much as studying how complex networks of molecular reactions make life do what it does. So this is just one of the many aspects of biology, but they found that they needed 3 different graphical languages to satisfy what they wanted to do. So activity flow diagrams, entity relationship diagrams, and something called process diagrams. So I won't go into these in much detail, but the activity flow diagrams show a flow of information between different entities. So I have someone who's working on this project, whose name I will definitely not reveal. He sort of derogated these diagrams a little bit. He said, these are just the diagrams that biologists like to put on their PowerPoint presentations. So I haven't been trying to understand these as much, although I should, but I just haven't had time. They're entity relationship diagrams show how different entities influence the behavior of each other. And these apparently can be translated into actual models, rule-based models, which say, if this is doing this, then that can do that. So if-then type models, logical, you could say, models of biological systems. But the ones that I find easiest to understand are process diagrams, and these show how entities change from one type to another over time. So these little boxes, which you probably can't read, are different kinds of molecules. I see ATP, that's a familiar one to me. I guess I even know what H2O is. And they're turning into each other. These arrows mean that a molecule of some type is, in this case, being formed. And what's promising to me about these is that if you give numbers for the rates of these reactions, you can actually take one of these diagrams and translate it into a system of differential equations. Because I'm a mathematical physicist, as soon as someone says system of differential equations, I think, okay, good. Now there's something I can understand. So these process diagrams are pretty complicated, but they generalize something simpler called stochastic Petri nets. You can think of those as a special case. And I'm going to talk about them a bunch in part 2. This is part 0, and then there are 1, 2, and 3. So in part 2 I'll talk about those. So a Petri net is something like this. You've got some different kinds of things. Here I just, which are yellow circles. Here, to keep things simple, I just have one, amoeba, one kind of thing. And then you have various kinds of processes. Here, well, I called it fission, and then I called it here reproduction. Fission, where one amoeba turns into two, so you see 1 in, 2 out. And then I'm imagining a world where the amoebas are competing for some food, and so sometimes they won't both get enough food and one will die, so this process would have 2 in and 1 out. So what we've got here is a symmetric monoidal category, obviously, where we have objects which are like amoeba or a pair of amoebas, which no one has ever written this before, amoeba, tensor amoeba. And then we have morphisms, which are processes whereby one amoeba can turn into 2 or vice versa. So from a mathematical point of view, a Petri net is a way of presenting a symmetric monoidal category of a certain kind, one that's freely generated by some objects and some morphisms. So you start with some objects and you just go ahead and make up more objects by tensoring. So you start with this one object, amoeba, then we get amoeba, tensor amoeba, tensor amoeba, tensor amoeba, blah, blah, blah. And similarly, we start with these basic morphisms and generate more of them by composing and tensoring and using the braiding, the things you can do in a symmetric monoidal category. So, like I said, from these generating morphisms, you can build all the morphisms in your category. And so here we've done a mixture of composing and tensoring to build up a more complicated morphism that starts with 2 amoebas and ends with 2, where first one produces, and then one of them competes with this one, loses the fight, and one comes out. So this should remind you of a Feynman diagram, and the point is, mathematically, it's exactly the same structure as a Feynman diagram, except we're not thinking of these as maps between vector spaces. We're thinking of them as morphisms in some other symmetric monoidal category. In a stochastic Petri net, we assign to each generating morphism a rate constant, which is the probability per time that it will occur given that the ingredients are present. And then there's a recipe, which I'll say more about, which lets you calculate a probability for any morphism to occur in any given amount of time. So if I knew the rate of fission and the rate of competition, I could ask, in 10 minutes, if I start with 2 amoebas, what's the probability that this process will occur? So this formalism is set up to do that. And the beauty of it is, to me, that the math behind it is almost exactly like the math of Feynman diagrams, where you're studying how particles, elementary particles, are interacting. But there's one huge difference, which is that particle physics is all about quantum mechanics. Quantum mechanics is all about complex vector spaces as objects. But probability theory is a different subject, and it turns out that you can just copy to a large extent, not completely, but you can copy what you did in quantum mechanics, but wherever you had complex numbers, which are these amplitudes that are always going on about in quantum mechanics, you can replace them with non-negative real numbers, and that's suitable for probability theory. So what this means is that we can take a lot of the mathematics that's been developed in quantum theory and apply it to stochastic processes. And I have a free book about that. Someday these slides will be, well, they already are. You can find these slides online, and then if you click on this blue thing, you'll get a free book about that subject, which you may or may not want, of course, but it's free, so it's not that bad. So I'm going to show you in part 2 how this gives us some new ways of thinking about chemistry, where these stochastic Petri nets are used a lot. But in chemistry, they don't talk about Petri nets. They don't use Petri nets. They use a different style of drawing the networks called reaction networks, which is actually completely equivalent, but it is more efficient in terms of saving ink. So here's a Petri net. Here's the equivalent chemical reaction network. This you probably like better because it's smaller. So here it says an A can turn into a B, and a B can turn into an A. Well, over here, that's true too. You have an A that can turn into a B via this process. You have a B, you can turn into an A, but it just takes up more space. So there's one community of people who studies Petri nets, there's another who studies reaction networks, but they're just different styles of conveying the exact same information. It turns out that the reaction network approach is actually very helpful for proving some deep theorems that chemists have proved about the dynamics described by these reaction networks. But they're mathematically, you could use either one. So I've been talking about, very roughly, about categories where probability theory is involved. So, as mentioned, that you take the categories using quantum mechanics and you replace complex numbers by non-negative real numbers, you get a good formalism for describing stochastic processes, random processes, but which don't involve any of the funny quantum phenomena, but just use classical probability theory. These kind of categories have been really fascinating to me, partially because all the really smart mathematicians who know category theory in physics, they're all busy applying it to quantum physics. In fact, I'm here invited by a center of such smart people. So it's very difficult to come up with new ideas in that subject, at least for me. So I say, okay, I'll switch to talk using the same kind of tricks, but to think about classical probability theory or old ideas, because for some reason that's less popular. So one very important concept in probability theory is entropy, Shannon entropy, or sometimes called information. And I've been thinking about that from a categorical point of view. So I think I'll state a theorem just to keep my cred as a mathematician up to snuff. So here's a category of where the objects, so it's called fin-prob, because the objects are a finite set with a probability distribution on it. So that's a very basic concept. You have some coins, you flip them, you have the probabilities of doing different things. You have a finite set of outcomes. Each outcome has some probability, which is greater than or equal to 0, and they add up to 1. So this is a subject, this is a kind of object studied in probability theory, very simple. What's the morphism? There are different kind of things you can pick as morphisms, but here what I'm going to do is I'm going to have a morphism be a function. So the morphism is perfectly deterministic. It sends any particular element of x to an element of y, but it preserves probabilities in the sense that the probability that your output is y is just the sum of the probabilities of over x, such that f of x is equal to y. So for example, if I flip some coins, I get a probability distribution on some set with 2 to the n elements. Then if I count how many coins come up heads, I'm mapping that set to the set of numbers from 1 to n. And this would be a kind of, and then I could calculate the probability that I got 6 heads. So that's a very basic category. What does that have to do with entropy? Well, it turns out there's a way to think about entropy in terms of that category. It turns out you need some structure in this category. You need to notice that if I have 2 sets with probability distributions on them, I can make up a new set, which I think of as a convex linear combination. What it is it's just a disjoint union of those 2 sets. The reason why I'm writing it in this funny way is that I make a new probability distribution on the disjoint union to be some number c times the first probability distribution plus 1 minus c times the second one. So that will be a probability distribution on the disjoint union because the numbers will all add up to 1 because c plus 1 minus c is 1. So for example, if I flip a coin and then use that decision to decide whether to do some random thing or another random thing, if my coin has probability c of landing heads up, I would be doing this construction. to get a probability measure out of two others. Turns out that you can also define convex linear combinations of morphisms. I guess I won't explain how that works, but it's actually, well, I guess I will. It's so simple. It's just if I have two sets here and functions from each of them to some other two sets, I just get a function from their union to the union of those two sets. So the number c doesn't show up in that at all. So there's this thing that Shannon invented called entropy, which is a number that you can calculate from a probability distribution. It's minus the sum of p log p over all your elements in your set. This tells you how much randomness there is in your probability distribution, how much information you would need to say the outcome of a random event if at first all you knew was that it was randomly distributed according to p. So for example, if p is 0 everywhere and 1 at one point, then the entropy is 0, meaning that there's no uncertainty, no randomness there. Whereas entropy is maximized if all the probabilities are equal. So people have known that it's a wonderful concept and have proved lots of theorems about it, so you might wonder why I'm asking such a stupid question. But the question I'm asking is, how can you see entropy emerge naturally just from the study of this category I'm talking about, of finite sets with probability measures on them? Where does it show up? Not because you know about coding or other things, but just where does it show up in the math? So here's one answer to that question. So entropy is a number. This is a non-negative real number. So we have to bring the non-negative real numbers into the game somehow. And the way I'll do it is I'll think of those non-negative real numbers as a category. This is a sneaky category theory trick, where you think of a category that has just one object, a boring object, but lots of morphisms from each of itself, which are just all the numbers that are greater than or equal to 0. And composing them, doing one morphism after another, is just adding. So you can take a humble entity like this with addition and just think of it as a category in this way. And the point is that that lets you get it talking to some other category, like this one. There are maps between categories. And a map between categories is something that sends objects to objects, morphisms to morphisms, and preserves composition. And it turns out that if you have any map between categories that's continuous, so if you change the probabilities a little bit, the number changes a little bit, and it preserves convex linear combinations, so you can talk about convex linear combinations here, but you can also talk about convex linear combinations of numbers. C times one number plus 1 minus c times another number. So you can talk about this map preserving convex linear combinations. If it has those properties, it's got to be a multiple of the change in entropy. It's got to be that there's some number, alpha, such that if you have any morphism in FinProb, this functor assigns to it alpha times the change in entropy. So entropy is in some sense the most universal way of talking about how much something is changing when you're doing a deterministic process to send one random variable to another, if you want it to be continuous and preserve convex linear combinations. This is a fun theorem because this function here looks sort of weird, right? It has logarithms and stuff in it in a funny way. These assumptions here don't seem to say anything about those funny functions, but it shows you why those funny functions come up when you learn the proof. I really think that there should be a lot more to say about this whole subject because entropy is fundamental in chemistry, and the random processes I'm talking about with these chemical reaction networks always have the property that entropy increases. And here I'm starting to use categories to think about entropy, but I haven't, and as far as I know, no one has yet connected them up to actually connect up these ideas with the second law of thermodynamics, that entropy under certain circumstances must increase. I think that's very important because when we're studying complicated systems, we want to use, as much as possible, very simple general facts to extract information about them, even if we don't know all the details. And it's been known for ages that one of those facts is the second law of thermodynamics. You can tell right away that certain kind of things won't happen if you know the second law of thermodynamics, and you don't need to inquire into the details of the device that's supposed to violate the second law. You just know that it can. And so understanding complex networks in ecology and chemistry should be connected to this stuff really involving entropy, but that hasn't been done. So what I'm giving you is a kind of picture of different things you could do with networks and categories, but the little pieces of the picture that I have so far, they haven't really been all fit together yet. That's why I want help. So I've been using networks to describe processes, like Feynman diagrams, and in category theory language, that makes us treat them as morphisms. But you can also just think of a network as a thing of some sort, and that gives you a different attitude towards them. In category theory language, it would make you treat it as an object. Object is a mathematical thing. So there's a lot of network theory that does that thinks of networks as objects. And since a network is a graph, for starters, but then with the vertices and the edges labeled in various ways, they use a lot of graph theory. So for example, here's a picture of a tiny portion of the internet from 2005. And it's clearly some beautifully complicated, intricately structured thing. I have no idea what this is, but something in the middle there is important. You can tell right away, right? You want to know what that thing is there. So people a lot of people working on network theory will take graphs and calculate various invariants of them to determine properties of their connectivity, how likely it is that if you add a new vertex that would stick onto a given vertex and so on. They're all treating these networks as objects rather than morphisms from a mathematical point of view. And you can see this interplay between networks as things and networks as processes very clearly in control theory. So control theory uses certain networks called signal flow graphs to describe physical systems that have inputs and outputs. So if you take a course on control theory, which unfortunately I've never done, a problem that you have to solve is the problem of how to design write a program that will move this cart back and forth by pushing on it with a force in such a way that this upside-down pendulum doesn't fall over. So in other words, control theory is about trying to adjust the inputs to a physical system to make it achieve a desired output, and balancing something on your finger is a good example of doing that. And this is a simplified version of that. So whereas classical mechanics, the way I learned it in school, is mainly about physical systems that don't have anything from the outside affecting them. Control theory is the branch of classical mechanics which focuses on how physical systems interact with things from outside. Of course, if you ever build a machine, that's what it's got to do. It's got to interact with things outside itself, or there's no use. So here, the interaction from the outside is the force that we think of as the user being able to adjust. So we have the position of the cart given by some variable x, and the tilt of this pendulum given by some angle theta. So in control theory, you learn, apparently, how to translate that into this picture here, which is the signal flow graph for that cart. So here the force comes in, that's the input. It gets duplicated, that is, you make two copies of this particular function. You don't, just a mathematical operation. One of them you multiply by 1 over m, and if there was nothing else involved, you would integrate it twice, and you get the position of the cart. So that's F equals ma turned on its head, figuring out the position of something based on the force. But the rest of this stuff comes from the fact that you've got the pendulum there. The pendulum is also affected directly by the force, but in a negative kind of way. Right? So if you push it this way, and then it flips back that way. So you get a minus sign coming in here, and it gets integrated twice. But when the pendulum tilts, that means that the force of gravity starts pulling the pendulum down more. So the actual tilt of the pendulum feeds back and affects the pendulum. And also, as the pendulum tilts, it pushes on the cart. So the position of the pendulum also feeds back and affects the force on the cart. So this is a picture of how the different parts of the system are interacting with each other. And the idea is then, it's a mathematical description of how to take any function of time that's the force and get the functions of time that are the position of the cart and the tilt or the angle of the pendulum. So that's, I think, a beautiful way to think about classical mechanics that I never learned in the classical mechanics course. So clearly category theory should be used to understand what is the category whose morphisms are pictures like this. And so I've been working on that with Brendan Fung here and Jason, other grad student of mine. And so we'll see when I give part one of this talk that these signal flow graphs describe morphisms in a very beautiful symmetric monoidal category. And it's similar to the one used in particle physics, that is vector spaces and tensor product, but it's also different. It's not that. It's linear in flavor, but it's different. But notice that when we call these diagrams morphisms, we're thinking of them as processes. We're thinking of them as a way to turn some input signal into an output signal. But the point is that you could also want to think of them as things, because signal flow graphs that implement the same process could be very different things. You could build two machines that do the same process, but are different machines. For example, if I wanted to build a machine that would take two inputs and switch them, well, I could build this. That would be the smart way to do it, right? Just switch them. But I could also do this. I could duplicate each of those inputs. This delta here means duplication. I could add them here, multiply these copies by -1, duplicate this, add them there. If you work it out, you see that if you put two numbers or two functions in the top, by the time they pop out at the bottom, they'll have been switched. So if you're doing category theory, you say these are the same morphisms. They accomplish the same effect. But if you're doing electrical engineering or designing a system, you would not want to think of these as the same thing. This is a simpler implementation than this. So we have to somehow reconcile these two attitudes. And the way to reconcile it is to go up one notch from category theory. Category theory is just the start. It's a dangerous subject to get involved in because it's always just the start of something that keeps growing and growing. And the first thing that comes after categories is bicategories, which have an extra level. They have objects, they have morphisms between objects, but then they have two morphisms, things that go between morphisms. And what we would like to say, the reason why I would like to use bicategories here is because I would like to be able to talk about, for example, a simplification process that takes this machine and simplifies it to this machine. Takes some morphism and turns it into some other morphism. So people who are designing electrical devices have a lot of rules about when you can replace a certain portion of a machine with some other thing and have it still work the same way. So those are really two morphisms. And so the point is, if a network is a morphism between objects, we can on the one hand think of it as a process of going from one object to another. But we can also think of it as a thing which is subject to further processes of its own, which are these two morphisms. So I think that attitude will let us bridge the gap between the people who like to use these diagrams just as names for functions or processes of other sorts, and people who treat them as actual physical things. So I believe that not just categories and bicategories are going to pervade network theory, or precisely. They already do, but we haven't quite gotten around to thinking about it. Now, I must admit that I've thought about this in an earlier incarnation. Back when I was working on quantum gravity, there was an approach to quantum gravity where people were interested in things called spin networks, of which this little graph here is supposed to be like a little portion of one. And the idea was that to understand the structure of space at the quantum scale, we should think of it as a quantum superposition of lots of spin networks. And then when people were starting to try to understand the dynamics of how things change with time, they started drawing pictures like this, where a network would change to another network. Because these things start looking like soap bubbles, they call them spin foams. And that was actually a bicategorical idea. There's a category where the morphisms are spin networks, and then a bicategory where the two morphisms are the spin foams. So people are still working away on this quantum gravity, this approach to quantum gravity. I don't know if it's ever going to work or not. Quantum gravity is a really hard subject. But the math involved is definitely very nice. And so one of my secret motivations, I guess, is to try to use that math for something more practical than quantum gravity, where we have no experiments and probably never will in our lifetime, my lifetime. Whereas if we think about something like the internet, we do definitely have a graph that's changing with time in interesting ways, and it's just ready for some of the same mathematics to apply to understand it. So I think I'll stop there. Thanks.
Thanks very much, John. We have some time for questions.
Yes.
So you mentioned a lot about physics and biology. Could you maybe say a few words about the role of computer science and how you see it fitting in this framework?
So computer scientists have much more than biologists already been using category theory, as you know, for studying processes. And so I tend to think of that. So for example, if you take the idea of a flow chart as some kind of network describing a process where data comes in, gets processed in various ways, and data pops out. That's something that people have known about for ages and have formalized to a fair degree. So I think of computer science is to some extent a kind of role model for other sciences that study complex systems made up out of interacting parts, in the sense that they already have some of the mathematical tools that can be used there. One thing that I find, so that's the good news. The bad news is that one thing it's not bad, but something that could still be done better, I think, is the use of bicategories in computer science. So I was talking about this over lunch, so anyone who had lunch with me can fall asleep now. But when I first heard about the lambda calculus and Cartesian closed categories, I was fascinated, because the lambda calculus is some kind of framework for modeling computation. It's a very simple, abstract model of a computer language. It's so simple even a mathematician can understand it. And some mathematician, actually, who couldn't understand it, tried to reduce it to category theory, which would be easier to understand if you're a mathematician, and came up with this discovery that lambda calculus is very related to a certain kind of category called a Cartesian closed category. So when I first heard about this, I didn't understand anything beyond what I just said. I thought, wow, that's great. So these computer scientists and category theorists have figured out how you can think of a computer or program calculating away some kind of morphism in a Cartesian closed category. So I should learn that stuff. But I found, to my disappointment, that the morphisms in the Cartesian closed categories that these guys were thinking about did not describe the process of computation. They were being used in some other way. So they would think about things like data types, and they think of a program as something that takes in some data type and output some data of some other type. That sounds good so far. There's a morphism between objects. But it turns out that if you had a program, for example, that took no input at all, that's an example, very boring example, no input at all, and prints out the number 100, that would count to them as the same morphism as a program that would multiply 10 and 10 and then print out the output. So the process of computing 10 times 10 and reducing it to 10 was completely buried in this formalism. You count those as the same thing, which is bad, because that's what computation is all about. It's the process of taking something, simplifying, working away on it. So what you really should do, and some people have realized this, is you should think about two morphisms as the process of calculation. This could be some complicated program that hasn't run yet, and this could be some program that, this is the running of it, and then when it's done, this is the program that prints out the answer. And so they should really be working with Cartesian closed by categories. And there's some people who know that. But the fact that that the people who've used category theory to try to understand the lambda calculus have buried the part that's what people in lambda calculus think of as like the interesting part, suggests there's a lot of room for development. Yes?
So you said you replace, when you're doing physics, you're using complex numbers, you're working over the complex numbers, and then the biological examples, you're working over the positive real numbers.
Yeah, any probabilistic example is what I meant.
When I just look naively at complex numbers versus positive reals, I think, well, complex geometry versus tropical geometry. Is that the right thing to think, or?
I don't know. For me, the structure on the non-negative reals that I'm using in probability theory, it's just ordinary addition and multiplication of numbers. It's not the tropical rig. So that's not showing up in this probabilistic stuff I'm doing. However, there is that tropical rig out there. So that's a funny other thing you can do with non-negative real numbers, where to add them, what you actually do is you you take the minimum of them, and to multiply them, you add them. That's really confusing. So you use plus and min instead of times and plus. But it turns out that, so one place I've seen that get used in very practical work is in things like railway timetable scheduling. When you're trying to figure out how long it takes to get from here to here, there are lots of routes you can take. For each route, you have to add all the times, but then you take the min over all possible routes to find the shortest possible route. So when you're trying to go from one city to another and then to another, what you're actually doing is you're doing matrix multiplication, but in the tropical rig. And there's some people who actually know that and are using that. So that's where I think that will show up, is in minimization problems.
Any more questions? Samson?
John, I think I must disagree with your remarks
Okay.
about the lambda calculus. I'm not at all arguing about the fact that maybe a good idea to look at bicategories, but the sort of example you gave, I mean, it's actually, I think it's blurring the distinction between a so-called extensional or well-pointed Cartesian closed category in the general case. If you're looking at a particular kind of extensional or well-pointed Cartesian closed category, the kind of identification you mentioned to take place. If you decide to actually know some interesting examples which do make that very distinction, actually even some of them are even well-pointed if you're willing to take account the fact that your input might be undefined, so that your attempt to multiply, but I mean, but there are certainly plenty of examples known and used by computer scientists because they're interested in looking at the processes of computation which would not make those identifications. And Cartesian closed categories do provide scope for that. So I think, yes, bicategories are good too, but you know, one shouldn't
Yeah, I was
mistake the...
Okay, yeah, due to my ignorance, I was getting carried away, but I think it's this idea of reduction, alpha reduction, beta reduction, and so on. Those processes, I like to think of them as two organisms.
So that is a very natural
I want them to
thing,
be
really.
in there, not sort of modded away as being made into an equivalence relation. So that's a more accurate way to say what it is that I want. What we need. About that. Yes?
You mentioned these slides were available online somewhere.
Yeah. Right. If you wait half an hour, it will be available probably just by typing in John Buys. They'll be on my main web page.
No, they already are.
Yeah, I think
Well, they're there, but they're slightly hidden. Yeah. So, but they'll become very visible in a couple of minutes. I just forgot to stick them out in front.
The link straight off is Google+.
Yeah, they're different. Yeah, if you type John Buys network theory, maybe you can already find it. But anyway, I'll make it easier.
Any more questions? Okay, in that case, everybody is warmly invited to come to our corner room. We may overburden the resources. We have a small supply of chocolate biscuits.
Let's do it. Let's fight.
But please come and continue the conversation in the corner room. Let's thank John very much for the great work.